All right, so this is going to be the first lecture for Chapter 10 on the gases. I'm going to apologize in advance for the background noise, the blower in the room. There's no way to turn it off, so I'm going to try to talk as loudly and as clearly as possible. So looking at Chapter 10, discussing the gases. First of all, some characteristics of gases. Unlike their liquid and solid counterparts, gases are able to expand and fill up their containers. The molecules of a gas will spread out. And also because they do spread out and there's lots of space in between the molecules, they're also highly compressible. That means that you can force the molecules back closer together by applying pressure. And then they also have, because again the spacing is so great between the molecules, they also have extremely low densities. So far, far lower density than any solid or a liquid is going to be the density of a gas. And so gases are, they follow a model that's called the kinetic molecular theory, and this helps us to understand the way the gases behave and what is actually going on with the individual particles of a gas as the different environmental conditions are changing in which you find the different gases. So the first tenet, or the first part of the kinetic molecular theory, is that gases are made up of very large numbers of molecules. Millions and millions of molecules can occupy just a very small space. And these molecules are constantly moving. They're in continuous random motion. Next is that because of their size being so small, gas molecules basically don't take up any space. If you were to combine the volume of all the molecules of the gas together, that would be basically negligible or almost non-existent when you would compare that to the total volume of the container in which you had the gas. So all of the particles themselves basically don't take up any space at all. And then finally, unlike with solids and liquids, there aren't any attractive or repulsive forces between the molecules. Okay, they are there. You can't say that there aren't any forces between the molecules, but they are extremely, extremely weakly attracted, weakly repulsive to one another. So basically, again, you can say that it's negligible. And then the collisions between gas particles are what we refer to as elastic. That means that energy is transferred whenever two molecules of a gas collide with one another, but the average kinetic energy of the molecules doesn't change. So for example, if you are in a car and you collide with another car, there's obviously going to be a lessening of the kinetic energy. Your two cars are going to stop because of that collision. But with gas molecules, when they collide with one another, the gas molecules basically bounce off one another without losing any energy whatsoever. So that is called an elastic collision. Okay, and then the kinetic energy of a molecule of a gas is proportional to its absolute temperature. So basically you can see as you raise the temperature of a gas, it is also increasing the speed of the gas molecules. Now notice there's a key word in this little tenet, and that is the absolute temperature. So here we're talking about temperature on the Kelvin scale, not Celsius or not Fahrenheit. The speed of the molecules and their kinetic energy is only proportional to the temperature when it is expressed in Kelvin. And so that's going to become very important as we get into the actual mathematical calculations that we're going to do in this particular chapter. Okay, so let's look at an example. So what is going to happen to the gas in this particular container when we alter the environmental conditions? So in A, we're going to cool the gas down. So we're going to take it from 298 degrees Kelvin to 260 Kelvin. And the piston's going to remain in the same place. So if we cool the gas down, that means that the gas molecules are going to be moving at a slower pace. They're not going to be moving with as much energy. And so gas pressure actually occurs whenever the molecules are colliding with one another and colliding with the walls of the container. So if they're moving with less energy, that means that the pressure is going to decrease. The collisions aren't going to be as forceful as when the temperature was 298. In B, if we move the piston and push it down and reduce the volume to half of what it originally was, that means there's going to be less space for the molecules to move around. So with the molecules having less space to move around, there's naturally going to be more collisions, more colliding with other molecules, more colliding with the walls of the container, and so that is going to increase the pressure of the gas. And last, if we use the little inlet valve and inject more gas into the container, then again, we're going to be increasing the number of collisions. There's going to be more particles of gas in the container, so more collisions with the walls, more collisions with one another. So in number one, that would decrease the pressure. In both B and C, that would increase the pressure of the gas. All right, so as we said, pressure is the amount of force that is applied to an area. So when we're talking about gases in a container, that force is the force of the collisions that are occurring between the molecules. And when we talk about atmospheric pressure, we're talking about the weight of the air per a particular unit of area. Okay, so normally we refer to atmospheric pressure in a term that is referred to as atmospheres. Okay, so atmospheres, 1 atmosphere is considered standard atmospheric pressure at sea level. Well, there's some other ways to express that. Here in the United States, we use the English system, and so we talk about PSI, which stands for pounds per square inch. There's also kilopascals, and then there's also mmHg, stands for millimeters of mercury, and also torr. Torr came from the scientist Torricelli, and then also expressed in terms of millimeters of mercury, which is more of a barometric pressure reading, which it has some applications in meteorology. Okay, and then also bars, that's another one that is sometimes referenced in this particular chapter. Again, it's more of a meteorological type of a unit for expressing pressure. The kilopascals one is more physics, but we will use that a little bit in this class as well. Okay, so how do you measure pressure? Pressure is measured with an instrument called a barometer. And so they are literally measuring the height in millimeters that the mercury in the barometer moves as a response to the pressure. So as you apply pressure, that's going to force the mercury higher up in the barometer, and so you are reading the height of the mercury, thus the units of pressure, millimeters of mercury. And again, you can see Torricelli was the person who named this instrument, so that is why we sometimes refer to these units as torr. Okay, so let's do a conversion. If we're going to convert 1.5 atmospheres to both torr and to kilopascals. Okay, so we are going to be calculating the pressure, 1.5 atmospheres, and we want to convert that to units that are torr. So we use our conversion factor. We saw in the notes that 760 torr is equal to 1 atmosphere. So in this case, the units cancel. 1.5 times 760, you end up with 1,140 torr. So 1.5 atmospheres is equivalent to 1,140 torr. Okay? If we are going to then go and find that in kilopascals, 1,140 torr. Again, from our relationship that we saw in the notes, 760 torr, which is, again, atmospheric pressure at sea level, is equivalent to 101.5 kilopascals. Again, the torr units are going to cancel. So you take 1,140 times 101.5, divide that by 760, and you get an answer of 152.25 kilopascals. Okay, so continuing on, after our example problem. Another way for measuring pressure is using what's called a manometer. So this is a device that used to measure the pressure of gas that is contained inside of a vessel, another container. So it uses the difference between atmospheric pressure and the pressure that is inside of the container. Okay, and from this we can get a definition of a unit that is called the standard temperature and pressure, or abbreviated STP. So STP is a set of conditions defined by 0 degrees Celsius and 1 atmosphere, or standard atmospheric pressure, that chemists can use when working with gases. And so an important relationship here that will become more important as we get further on into the chapter is that it does not matter what type of gas you're talking about. We could be talking about carbon dioxide, hydrogen gas, nitrogen gas, water vapor, but any gas, if you have 1 mole of that gas, it's always the same volume at standard temperature and pressure. It's always 22.4 liters. That's called the standard molar volume of a gas. All right, so we're going to investigate some things that you looked at before in your first year chemistry class. It should start to jog your memory. We're going to talk about some of the gas laws. And here we're going to be comparing the temperature, the pressure, and the volume and the moles, or the amount of the gas. So the first law we're going to look at is called Boyle's law. So Boyle discovered that the volume of a fixed amount of gas at constant pressure, that means you're not changing the pressure, at constant temperature, where the temperature remains the same, is inversely proportional to the pressure. So what that means is that as the volume increases, the pressure is going to respond inversely. So volume increases, pressure goes down. Or if the pressure increases, the volume goes down. So if we were going to plot a curve of the volume versus the pressure, you would get a curved line. However, if you were to plot the inverse, so the volume versus the inverse of the pressure, that would give you a straight line. So you can see that there is a inverse relationship. And so whenever we have an inverse relationship, that means that if you multiply the two values together, it's going to come up with a constant value. That's what the K represents in that equation. Okay, the Charles law then is relating the volume to the temperature of a gas. So if you have a fixed amount of gas at a constant pressure, it is directly proportional to the temperature. So again, the key word here is the absolute temperature. So it's only the temperature in the Kelvin scale that is directly related to the volume. So whenever volume increases, temperature increases. Whenever volume decreases, temperature decreases. So again, because they are directly related, it is the division, the volume divided by the temperature, that is equal to the constant value K. All right, so if you plot volume versus temperature, you will get a straight line. Okay, and the final law we're going to look at is called Avogadro's law. Avogadro's law relates the volume to the amount of moles of the gas. So again, this is a directly proportional relationship. So when you take volume divided by moles, you come up with a constant. Okay? So let's do another example problem. In this example problem, you notice that the volume and the pressure is what we're investigating. So if we're looking at the volume and pressure, we're going to be using Boyle's law. And the equation that we can use for Boyle's law is this one. P1 V1 equals P2 V2. So in this case, the P's represent the pressure and the V represents volumes. And then the subscripts 1 and 2, that stands for like the initial pressure and the initial volume, and the second or the final pressure and the final volume. And I'm going to suggest that when you do these problems, that you kind of make yourself a table to make the solving of the problems easier. So as you go through and as you read through the problem, what you're going to see is that the first pressure that is discussed, 748 torr, and it tells us that the volume is 4.50 liters. And the pressure is 557 torr. All right, so let's take a look here at example number 3. So we have a balloon that has a volume of 450 liters and its pressure is 748 torr. So we want to know what is going to be the volume of the balloon when we change that pressure to 557 torr. So I'm going to suggest that when you do these kind of problems, that you start off with a chart to kind of help you organize your information. So this is Boyle's law. So the equation for Boyle's law is P1 times V1 equals P2 times V2. So make your chart down the side of your different variables. So as you read through the question, you can plug in the different variables. So first of all, we have a volume of 450 liters, so that is volume number 4.5 liters. We have a pressure of 748 torr. And we're going to change the pressure to 557 torr. So if we change that pressure, we want to know what is the new volume. So I'm going to plug these variables into my equation. So I have 748 times 4.50 equals 557. And I'm trying to find the second volume. Okay? So to solve this algebraically, I'm going to divide by 557. This will cancel. And so our volume is going to be 748 times 4.5 divided by 557, which works out to be 6.04, and the units are going to be the same as the units on B1, which is liters. So there is our answer. So then we can also look at this and see, does that answer make sense? So if we remember the relationship between pressure and volume, we know that whenever the pressure decreases, okay, the volume should respond inversely. So the volume should go up as the pressure goes down. So in fact, we can see that that is the case. 4.5 increases up to 6.04 as the pressure decreases. In our next example, we're going to look at the relationship between the volume and the temperature. Okay? So as we go through this equation, we see that we're talking about a temperature of 24 degrees. We have a balloon, and the volume of air in the balloon is 2 liters. However, when we take that balloon outdoors where the temperature is colder, 12 degrees Celsius, there is a change in the volume. So here the relationship between volume and temperature, remember, is a direct relationship. So that means that our equation is going to look like this. Okay, again, I recommend that you make yourself a chart to help keep all of the numbers organized. So first of all, the temperature is 24 degrees Celsius. That's going to be T1. So remember, the relationship here between the volume and the temperature is referring to the absolute temperature, the temperature in the Kelvin scale. So we have to convert 24 degrees Celsius to Kelvin by adding 273 to change that to the Kelvin scale. So this is going to end up being 297 Kelvin. And the volume is 2 liters, so V1 is 2 liters. We want to know what the second volume is, what the new volume is when we take it outdoors, where the temperature is 12 degrees Celsius. So again, add 273, and that gives you 285 Kelvin. Okay, so we plug this into our equation. 2.00, T1 is 297. We're looking for V2, and T2 is 285. Okay, to solve this kind of problem, we're going to employ what is called cross multiplication. So we're going to do that kind of thing, okay? And so whenever we do this, we're going to have 297 times V2 is going to be equal to 2.00 times 285. And then we can divide both sides by 297. So if you do that, then you're going to get an answer of 1.92. And since volume 1 was in liters, volume 2 will also be in liters. So again, at this point, we can look at that and kind of just figure out, does that answer make sense? So we know that volume and temperature are directly related. So in this case, the temperature is decreasing, so you would expect the volume to also decrease. And so you see that it does. It goes from 2 down to 1.92. So that answer would make sense. So as we continue on, we can see that sometimes it requires that you are going to combine both the relationship of Boyle's law and Charles' law together. So you can use both of those to predict changes in any of the other parameters, be that the pressure, the volume, the temperature, or the number of moles. You can combine them. So this is an example problem where you're actually going to be combining all three variables, the pressure, the volume, and the temperature. And in this case, we're going to use something that is referred to as the combined gas law. So as we use the combined gas law, okay, so it's going to include the Boyle's law, P1 and V1, but it's also going to include the Charles law as well. So we're also going to put the temperature in there. So this is the equation for using the combined gas law. So again, we want to make our chart. Okay, so as we read through the equation, it says an inflated balloon has a volume of 6 liters, so that's our first volume, at sea level, which is defined as 1 atmosphere, so our initial pressure is 1. And it's allowed to ascend to an altitude where the pressure is 0.45 atmosphere. So this is our second pressure reading. Okay? During the ascent, the temperature of the gas falls from 22 degrees Celsius to negative 21. So our gas begins at 22 degrees. We have to, don't forget to change it to Kelvin. So that is going to be 295. And then when it gets higher in the atmosphere, the temperature is much colder. It's negative 21. So if we change that temperature to Kelvin, that gives us 252. All right, and it wants us to calculate what is the volume at that new altitude. So we have everything we need except for V2. So we're going to plug into our equation again. 1.0, 6 liters. T1 is 295. Second pressure is 0.45. We're looking for the second volume, and the second temperature is 252. Again, we're going to employ our cross multiplication method for solving. So 295 times 0.45 times volume 2 is going to be equal to 1.0, 6.0, and 252. So then, to get volume 2 by itself, we're going to divide both sides by 295 and 0.45. These cancel, leaving us with just what volume 2 is going to be equal to. And so if you do that, that comes out to be 11.4 liters. So you can see here, there really is no difference to the way that you solve the problems, be it a simple Boyle's Law or Charles' Law or a combined gas law problem. You just simply plug in the values that you know, and then you, I call it plug and chug. You plug in the numbers and you solve the equation to get to your final answer. Okay, so far this is what we know. We know that there is an indirect relationship between volume and pressure. We saw that in Boyle's Law. We also know that there is a direct relationship between volume and temperature from Charles' Law, and also a direct relationship between volume and the amount of the gas in moles. That was Avogadro's Law. So we can combine all of those to come up with another equation, which is called the combined gas law, or called the ideal gas law. Now, there's another component to the ideal gas law, and that other component is called a gas constant of proportionality, and it's abbreviated with a capital R. And so the value that you would use for R comes from the unit of the pressure. So you can see here, if the pressure happens to be in atmospheres, then the numerical value of R is 0.08206. If the unit of pressure is in kilopascals, or that's what this meters cubed in kilopascals, that would be kilopascals, that's 8.314, okay? Or if we were using torr as our pressure, that would be 62.36. Okay, so depending on what the units of your pressure is, your value for R is going to be different. It will basically be one of 3 numbers in the types of problems that we're going to do. So we have this relationship, we add in the R, the gas constant, and then we come up with PV equals nRT, which is the ideal gas equation. All right, so let's look at another example problem here that uses the ideal gas equation. Okay, so for our ideal gas equation, we're going to use our PV equals nRT equation. And we're going to, again, make our chart. So it says the calcium carbonate decomposes and gives us calcium oxide and carbon dioxide gas. A sample of calcium carbonate is decomposed, and the carbon dioxide is collected in a 250 milliliter flask. After the decomposition, the gas has a pressure of 1.3 atmospheres. So 1.3 atmospheres, that is going to be our pressure. It also tells us that it has a temperature of 31 degrees Celsius. So 31 plus 273, that means our Kelvin temperature is 304. And I skipped right over our 250. So 250 milliliters is our volume. Now we have to be careful though. Whenever you're doing the ideal gas law, your volume has to be measured in liters. So 250 milliliters, if you divide by 1,000, is 0.25 liters. So in order for your units to cancel with your gas constant R, it has to be measured in liters. All right. So in this case, since our pressure is measured in atmospheres, the number that we're going to use for R is the 0.08206 number. And we're going to be looking for the number of moles. So we plug in 1.3, 0.25 for our liters. We're looking for moles, 0.08206, and the temperature is 304. So we solve that equation for N. We divide by 0.08206 and 304 here. These cancel. Divide by 0.08206 and 304 here. And so we get an answer of 0.013 moles. Okay, the second part of the equation, B, says, what would the pressure be if the gas is moved to a 500 milliliter container at 0 degrees Celsius? So, same equation, PV equals nRT. Okay? We're looking for the pressure, so we don't know what P is. Now the new volume, instead of being 250 milliliters, is 500, so that's going to be 0.50, that's the volume. We just figured out how many moles, 0.013. Okay, we want it in atmospheres still, so we're still going to use the same R value. And now the temperature is 0 degrees Celsius. So 0 degrees Celsius, if you add 273, is 273. Okay, so I would divide both sides by 0.5. And the new pressure now is 0.584